Okay, so last time we had this general setup where one has some data. Based on the problem at hand, you have some cost function or error function. And we imagined optimizing that with respect to some model of the data. And then we studied the properties of the learned model in terms of generalization and bias and variance and so on. And we kind of glossed over the fact that there's this first step that's pretty hard in principle, which is optimizing the objective function or minimizing the cost, right? And so I thought I would spend some time talking about how one goes about doing that these days. And one of the suggestions yesterday was to talk about learning dynamics. So I'll give some basics of learning dynamics here. And one of the questions yesterday was, why have we seen such an explosion of interest and activity in machine learning over the past 10 years? And I said we have a lot more data and a lot more computing power, and that allows us to use certain kinds of models that didn't work when they weren't at that scale. And this generally goes under the term deep learning or deep neural networks. And you might ask, what is it that defines something as being part of deep learning? There's feed-forward networks, there's recurrent networks, there's transformers, there's deep reinforcement learning, and so on. In some sense, the idea that unifies all of these techniques is that you have some model and some objective function that you can take the derivative of. And the buzzword really of the past decade has been end-to-end differentiability. And what that means is that then you can optimize the objective function by taking the derivative or the gradient and then following it and doing gradient descent or ascent, depending. So let me just say what that is. So last time we had some error function, which depends on the parameters for a fixed data set. And usually that error function is a sum over all of the errors on individual data points. So you have some data points xi, and you predict on each data point with your model a given set of parameters, and you just take the gradient of this and go in the opposite direction. So you define a vector v, which is scaled in some way to be the gradient. And then you update your parameters by just following in the opposite direction of that gradient. Okay? And this has all sorts of problems in principle, and it should be a priori surprising that this works so well. So for a complicated model, this cost function is going to be, in principle, highly non-convex. So doing this is going to depend strongly on where you start. It depends on how big the step size you take is, all these things. And it's not obvious that this should work well. And there are all sorts of variants of this method that try to mitigate some of the concerns. And I'll tell you a couple of them. But it turns out that for some of the models or many of the models that are used in the field of deep learning these days, you can do relatively simple things, and it works surprisingly well. And some of the more subtle ideas end up not being that important. Okay, so one of the big concerns is, well, you find the gradient, which tells you which direction the error goes down or up, and you have to scale it by some step size, so you update your parameters, right? And if you make this really big, you'll make a huge step, and you're at a new place in your error landscape, and that looks nothing like it did before. And then you do it again, and maybe you shoot off in some other direction, and the dynamics is very, very unpredictable, and you're not necessarily going down because the gradient is just a local property, right? So you would like this to be small, but if you make it too small, you'll never make progress. So you have to find some way of finding the right step size. And a really old idea goes under the name Newton's method. And I don't want to go into too much detail about this, but the idea...
I think this everybody has seen, right?
Yeah.
Am I being unfair? Who doesn't know what Newton's method is?
At this point, you realize what this is.
Yeah, I mean...
True.
Okay, go ahead.
So I'm not going to tell you to use Newton's method. You should not use Newton's method. You can't use Newton's method. But it's useful nonetheless to think about. So the idea is, imagine you take your error function and you expand it around the point that you're at to second order. So this is the gradient term, and this h is the Hessian, which is the matrix of second derivatives. What you would like to do is, if you imagine that you're locally quadratic, you'd like to find the v that minimizes this. And the way you can do this, I'm not going to write it down, is you take the derivative with respect to v and set it to 0, and then hope that you can find a point of the left-hand side where the gradient is 0, meaning that you found either a maximum or a minimum, right? And if you do that, you get 0 equals the gradient of the error plus the Hessian. Essentially defines this optimal v step that you want. So if you want to write down something like this, for Newton's method, what you would say is that the v that you need is the inverse of the Hessian, evaluated at the previous time step, times the gradient. And then you make a similar kind of step. And so you can see here that you need the inverse of the Hessian to make any progress. And for big models, so these days you can have a neural network that has 100 million parameters. So this is a 100 million by 100 million matrix. There's no way you're going to invert this, right? So this second order information is not going to help you. It's even worse, though, because with most of these models, when you are training them, if you can look at the Hessian, what you find is that there are a couple big eigenvalues of the Hessian, and then a huge C, a bulk of essentially 0 eigenvalues. So you can't invert the Hessian anyway. So this is a big problem, and you would never actually use Newton's method on a neural network. But the idea is that you're using this inverse of the Hessian matrix here to adapt the step sizes in different directions according to how fast the derivative is changing along those different directions. And this can give you some intuition for the right step size. So that's the main reason why I want to illustrate this. So if you imagine doing this in just one dimension, so the Hessian is just a number which encodes the curvature. So imagine you just have a quadratic function that you're trying to optimize. So this is just the curvature. Then you have sort of 3 different kinds of behavior. If you have a learning rate that is smaller than 1 over the eigenvalue of the Hessian, you'll take little steps down the quadratic bowl like this. If you use Newton's method, what you get is this, where in one step you go right to the bottom. And if you use a step size that's bigger than the Newton's method optimal, you start pinging back and forth across the bowl, but you still go back down to the bottom. But if you use a step size that's bigger than twice the optimal, so one times the optimal takes you right to the bottom. If you go twice the optimal, it takes you across to the other side. And if you go bigger than that, you start pinging back and forth outwards, and you fly away, and learning is unstable, right? So these are sort of different phases, if you want, of learning dynamics. And in one dimension, it's fairly simple. it's more complicated when you have many dimensions, because now you have different curvatures in different directions, and you're in trouble because the spectrum of the Hessian, as I was saying, has some very large eigenvalues, some very small eigenvalues, and you're sort of sensitive to the smallest one here, or the largest one. So if you have a whole spectrum, then the maximal learning rate that you should be allowed to use is going to be something like 2 over lambda max, right? So if there are very big eigenvalues in a lot of small directions, now you're making very, very small steps to make sure you don't go unstable, and you're not making much progress. Does that make some sense?
So here you're talking about a scheme in which you replace the inverse Hessian by a diagonal matrix, which is just your eta. And now you're asking what should you choose as an eta based on the spectrum of H?
Yeah, I'm saying that you can't actually do this for a real size model, so this is just intuition for what you would like to do, and over there. And so really, if you just stick with something like this, if you pick a step size that is bigger than this value, then you'll explode, and you won't make progress, right?
Okay, but you could also imagine using eta that's different for each direction without having to invert it.
Absolutely. So yeah, so this would do that for you, but you can't actually do this. There are methods. In particular, there's one called RMS prop. There's another one called Atom, where you get some juice of the second order information by keeping a running average of gradients and things like that. And that's the idea, to have different learning rates in different directions for this reason. And these were very popular for a while. What people have found more recently is that you will actually fit the data faster, but you won't generalize as well. And this is actually an active area of research for why that is. Yeah?
It isn't obvious to me, but why is beta greater than 2 beta optimal going to push it out? Like, is this empirical? Is it the fact that it's a quadratic bowl?
Yeah, exactly.
That can be derived?
Yeah, so I'm just saying that the optimal step size that gets you right to the bottom from some point is this big. And if it's a perfectly symmetric quadratic bowl, then if I go twice that big, I'll ping right to the other side of the bowl. Yeah. Yeah, that's all. OK. So another question? All right. So this scheme has this issue of how do you deal with this learning rate, and that's a hard problem.
What does generalize mean? When you said that you learn faster, but you won't generalize as well?
You'll fit the training data as well,
Okay.
but you won't perform well in the test data, or as well in the test data. So maybe it's maybe a good time to say that when people start going down the rabbit hole of optimization methods, it's easy to think that machine learning is just optimization once you set up the problem. And that's the wrong way of thinking about it in the context of last lecture, because what you really want to optimize is not the function that you have in hand, but it's something correlated with the function that's hidden to you that you don't actually have access to. Over-optimizing the thing you have in hand is essentially overfitting. And we'll come back to that. OK, so finding the right step size is a big problem. And additionally, as you make progress, this can take a very long time. The curvature that you're dealing with can be changing, and a common thing to do is have a schedule for the learning rates. So I wrote this as eta sub t because different steps of your optimization are going to have different etas, and you usually decay them exponentially in time or as a power law or something, and that allows you to sort of dig deeper down into tighter spaces. But again, you might overfit if you do that. OK, so another issue with doing this simple algorithm here is that to compute the gradient requires you to sum over all of the samples. And if you have a lot of data, that's not feasible. You have to compute the gradient many times, you have to sum of the sample many times, and that's too expensive. And if you're very far from the optimum anyway, maybe there's a thing that you can do to get some rough estimate of which direction to go without getting the exact gradient, and that will be good enough for now. So this motivated the idea of what's called stochastic gradient descent. So this is gradient descent. And for stochastic gradient descent, what you do is you break up your data into a bunch of random little mini batches of data, and you just compute the gradient on one random mini batch, and then you pretend like that's a good estimate of the gradient and continue. So just to write that down, and you replace the full gradient with a sum inside of data that are in some batch, kth batch of the gradient on those data points. And then once you have that, then you plug it in here and do the same thing. Does that make some intuitive sense? So this will give you a huge speed up in terms of computation. If you have a mini batch size of, say, 100, but your data has 1 million samples, you can do this much faster. And this sounds like kind of a boring idea. It was invented a long time ago to speed things up. But it turns out that it's actually quite interesting. And what you find is that when you do this, which is wrong, you actually perform better often when you try to generalize. So you make predictions on the test set. Yeah?
How do you choose the batch? Like, is it just like a random selection of the data points, or is there like a certain way of choosing like a good batch versus a bad batch?
So usually the best idea is to have each batch be sort of random sample with replacement of all of the data. Oftentimes people do sort of random shuffling and then chop it up into batches, so without replacement, but actually with replacement is better, it turns out.
So each time step you have a new batch.
That's right, exactly.
So your B here depends on root K?
Yeah, I should call that T then. Sorry. Yeah.
So you say you often do better using the stochastic gradient descent. So does that mean, in some sense, you're not really concerned with how good the approximation your gradient is? I mean, so like I could imagine like trying to check this empirically for a given data set. You take maybe as large a number as you can and you compute gradients, and then you check for different batches that have similar things. But maybe it's just not important to do that if it's just working better.
Right. Yeah, so in principle, yeah, what you suggest would be what you would want to do if you needed this to be a good approximation to the full gradient. But in practice, you don't need to worry about that because this seems to work better. The reasons why this seems to work better are, in some sense, an active area of research. I have a paper from a month ago trying to explain some aspects of this. And the kinds of intuitions you might have are that if you're doing gradient descent on all of the data, you'll easily get stuck in a local optimum. Whereas if you have this randomness that comes from stochastic gradient descent, then you'll have some extra noise that kind of looks like a temperature, so it'll allow you to tunnel out of local optima.
It's not something that looks like the simulated annealing.
Sorry?
It's something that looks like the simulated annealing. You add some noise and then the noise.
A little bit, yeah.
Relax.
Yeah. So a picture that people have tried to push for this is imagine that you have the true error landscape defined by the full gradient, and this looks like a Langevin dynamics on that full error landscape with some added noise. That's actually an incorrect picture, but in certain regimes, you can get away with using it. So it won't lead you astray if you're thinking about simple things. But what you really have for this dynamics is you have a landscape itself that is fluctuating up and down and moving in weird ways, right? You don't have a static landscape with additive noise, and there are times where that makes a big difference. And the idea of having this noise letting you tunnel out of local optima is also probably not what's making stochastic gradient descent work so well. Maybe as a sidebar, I'll give you my perspective on why this works better. So, yeah. That's another good question. So this is another parameter of your learning algorithm that, in principle, one can optimize by trying it out, seeing how it works, trying again, seeing how it works, having a validation set to see which is the best one, and so on. The best practices kinds of numbers are usually around 100 samples is a good number, but that's going to depend on the kind of data you have, the structure in your data. Yeah.
Does stochastic gradient descent increase the variance? Are you more likely to have spread in different models?
So if you initialize a bunch of models in parallel and you run, from the same point, and then you run stochastic gradient descent, yeah, they will find different solutions. So the reason why I was saying that, oh yeah.
Is it only this is non-dynamic is incorrect? Like, is it because you don't know like how to model the noise for your data set? So you rather like do feedbacking rather than
The reason is actually quite subtle, and it involves taking limits properly. There's a paper that I recommend called Fluctuation Dissipation Relations for Stochastic Gradient Descent by Shoya Ida that is very good on this point.
So is this an interesting sort of part of physics meets algorithms, or not necessarily?
Yeah, I think so, certainly.
You can't say more why, or?
So I'll give you a 2-minute sidebar on some work that I did using this fluctuation dissipation relation and why I think it's interesting physics. So what people have found is that for big neural networks that are what you would call over-parameterized, so you have many more parameters than you have data points, that would seem to indicate, in the context of yesterday's lecture, which I still have the slides here, that you're far over here on the model complexity side of things, and you shouldn't fit very well. And the test error, the out of sample error, is supposed to go up there. But what you find for over-parameterized neural networks is that this goes down, and then it just kind of stays flat. It doesn't go back up, and that seems very odd. And what people have realized through various kinds of experiments is that in addition to that observation, the error landscape does not consist of many isolated local minima. It's essentially connected. So if you find a minimum from one initialization, another minimum from another initialization, you can actually find a path connecting them that doesn't cross any barriers. So the landscape, rather than being glassy, looks like a big bowl where there's, or a big valley where there are a million dimensions that are flat, and then there are some upward dimensions, and you have to navigate in this flat valley. Yeah?
So there's a lot of algorithms which have been inspired by spin class systems.
Mm-hmm.
Can you use those for these large number variable optimization techniques?
Some of them you can, but since the error landscape seems to actually have a much different character than we thought it did, they're maybe less useful than we thought before. Yeah.
Yeah, so you really just deterministically go down, like, is there an alternative where you do, like, actually turn on temperature and do, like, Monte Carlo, like?
So in a not quite correct sense, you can think of this as having a finite temperature, where the size of the batch is inversely proportional to the temperature.
You don't take all your UI and XIs, you take only some subset.
Exactly, yeah. And if you make that a bigger and bigger batch, the temperature decreases because you're just following the actual landscape. Yeah.
So you're saying you have like a really flat valley with many flat directions. Is this the nature of the data that we're
So this is a research level question. It's to my mind, a marriage between the structure in the data and the structure of the model. And it only happens when these neural networks are very, very big. There are many more parameters than you should have had. So you should think of it like you're adding a bunch of redundancy in some sense, and the naive parameter counting for model complexity is not the right way to think about it. So you're adding a bunch of extra flexibility in the model that it's not taking advantage of. This will get me too far astray, but if you train on data that is not natural, that is randomized in some way, then the picture changes completely, and you actually do use more of that capacity. All of those extra parameters are being used, and the landscape looks different. So it's a combination of the data and the model that makes this look simpler. And it's an important component of why neural networks have risen in the past 5 years, that once you over-parameterize them on natural data, they don't overfit, and their optimization becomes easier because by adding more directions to move in, it somehow makes it more convex in a sense. But we don't really understand those statements rigorously. I think there was another question over here. Yeah.
So you said that in practice you don't see this E out going back up, so which means that the variance doesn't go back up. Could this be because you don't actually solve the optimization problem? Or is it really that if you really solve the optimization problem exactly, the variance still levels out?
So these models are so flexible that they can fit any data that you give them. So they will get zero error. They will perform perfectly. So you are solving the optimization problem that you set out to.
That's not I disagree. I think that's not what defines solving the optimization problem.
You're not solving the machine learning problem. You're solving the optimization problem that you're solving this optimization problem.
We get a true zero.
And if you're doing something like classification, yeah, you'll predict all of the classes exactly perfectly.
Okay, but if you're doing classification, then you don't have a continuous function like you did here.
Yeah, you can still have that. This is a function of the parameters, so you can.
Yeah, but how are you going to calculate the gradient of the classification error? It's not continuous, right? It's like a number.
We can talk about that when we go to neural networks. So you have a cross entropy loss or a generalization of that, or cross entropy. Yeah. Okay, so let me finish this sidebar here. So the landscape, rather than being very rugged, looks more like this, where there's a valley that is a million dimensional, and then there are some directions that are steep, right? And nonetheless, the curvature in the steep directions is a function of where you are in the valley. Sometimes it's pretty flat, sometimes it's pretty steep, right? And what a student of mine found was that the noise from stochastic gradient descent is colored in a way that it moves you from the steep area or the sharp area to the flatter area. And there's some issues with defining this and so on, but it seems like that's what the noise is doing, and you can think of it like an entropic force. Like if you're stuck over here bouncing back and forth because all the gradients are in this direction, you're confined. But if you're able to move this way, you spread out more and you have a higher entropy. So SGD is actually pushing you out in that direction. And this is good for generalization, roughly speaking, because again, what you're trying to optimize is not this function, but the thing correlated with this function. So it's going to be jiggled around in some way. And if you're somewhere where small changes in your parameters cause big changes in what you're computing, then as the actual problem gets shifted, you might perform very poorly. So doing it this way will actually give you a phase of learning where you're kind of slowly moving this way, instead of just pure gradient descent having you come down to the bottom of this valley and getting stuck. There was a question, so yeah.
We mentioned before that Adam or RMS or etc. are not good for generalization, or I guess to a certain extent. I don't know if that's an absolute statement. But they're built upon they're built after stochastic gradient descent, right? Like you could still kind of do the same thing. I mean, there's still noise in the system, so wouldn't it you're taking Hessian into account, then aren't you taking both, like noise
And curvature.
Yeah, your curvature, so like what?
Yeah. There is not a simple answer. So when you do things like Atom, you're trying to get estimates of curvature, which would be controlled by something either the Hessian or the Fisher information. But you do it in such a way that what you compute is really the covariance of the gradients, which is different. And as a result, actually, the motivation behind Atom is very suspect. And the fact that it works as well as it does is, at least to some people, surprising. But it turns out just experimentally that when you do pure SGD, it does better in most cases than using Atom. Yeah.
How is stochastic gradient descent behaving at saddle points?
At saddle points. So I don't have too much to say about that. Is it easier to get away from? In some sense, I imagine yes, because you're more likely to discover the downward direction. So oftentimes there are maybe only a few downward directions, or many fewer than there are flat and upwards directions. So having the extra sort of exploration of SGD to help you find those directions is, I imagine, useful. But I don't know anything quantitative. Yeah.
How much of this depends on the loss? So how much of this is specific to the squared loss versus?
So everything I'm saying here, one of the reasons I'm talking about this so early on is I haven't made any statement about what the loss is, what the model is. This is just sort of general concepts in learning dynamics. Certainly, it's going to depend on the loss, like the things I was saying about, when the loss has a certain kind of valley structure, you'll get some dynamics. When it's glassy, you get other dynamics, and so on. There's specific statements you can make for specific losses, but I can't say anything in full generality. Okay. So the other extra wrinkle that is often used, that maybe I'll say before I move on to other things, is let's see. So when you do stochastic gradient descent and you have just a couple samples, you're getting very different gradients every time. And what you would like is to sort of get a sense of what coherence there is in all of those vectors, right? So what you do is you add something called momentum, which you can rewrite as, if you make this Langevin sort of approximation, you end up with a particle with momentum. But essentially what you do, and maybe I'll just tack it onto here, is when you pick your new v, you at time t, you have some memory of what was happening before, plus learning rate times that. And this helps mitigate some of the noise. And also when you have very flat approximately flat directions, over time you'll get a sense of which direction is slightly downward, and you can make some progress. The prescription that is used all the time is using stochastic gradient descent with momentum and a learning rate schedule that is sensible, whatever that means. That's most use cases of optimizing models with gradient information these days. Yeah.
Do you have some physical intuition behind momentum? Because I've seen people use the argument of critical damping.
So we have a little section in this review where we make the analogy to a particle with mass. Yeah. But you should just think of it like that the information that you got on the last gradient step is going to be useful for this gradient step as well, because you didn't move very far. So you should keep some of that juice that you had before and add it to what's going on now. So you put a little gamma parameter here that's less than 1. So you get some of this and some of the new stuff. Does that make sense?
Well, no, I was wondering, how do you pick gamma?
Again, this is another what's called a hyperparameter of the model. It's a parameter of the learning or of the architecture or so on that you need to choose, and that you can in practice what you do is you pick a value, you do it, and then once you have your learned model, you test it on another data set and see how well it does, and keep iterating that until you find a good value. Yeah. So I don't have any good analytic answer for that.
No, but we want, like, a concrete answer. Do this, so we don't waste 3 months of our lives finding gamma. But you don't have that either.
I can't tell you that. I mean, that's why.
That's why we got you here, David.
That's why there are tons of summer interns in these industry labs to tweak hyperparameters. So I can't tell you that.
0.95.
What's that?
0.95.
Yeah.
0.9, 0.95, around there. If my answer to mini batch size is 100, gamma should be 0.9 to 0.95. Yeah. Okay. So I just wanted to give you a flavor of the kinds of issues that arise when optimizing functions via gradient-based methods, and the kinds of dynamics that can occur. I don't want to go into too much detail, and my goal here is to give you concepts, not to give you concrete prescriptions. So I'm going to move on to other topics unless there are other questions.
Yes, move on, move on.
Okay. So today's lecture is a little bit of a grab bag of things that we're going to need later. And the next topic is Bayesian inference. And I don't want to go into very much detail about Bayesian inference. I don't want to get into frequentist Bayesian debates and so on. I just want to tell you a couple of simple things, simple concepts, because questions of likelihood and so on came up yesterday. So I'll introduce the concepts. I'll illustrate them with a simple example, and then we'll move on to other things. Okay. So there are a few main concepts when thinking about doing Bayesian inference. And I'm going to just introduce them and not get into, as I said, any debates. I'm going to start with the easiest one. The first one is called the likelihood function. And the idea of a likelihood function is you have some data, and you look at the probability of that data given some setting of your parameters. And this likelihood function encodes your model. So your model and any noise that you assume and so on is inside of this likelihood function. So if you have that model, then you can plug in a value of the data point and say, oh, the probability of that data point was 0.2. There's no notion of the likelihood in the absence of a model. It's only in the context of a model with a chosen set of parameters that I can talk about the likelihood. Now, an important subtlety, which is not just semantics, is that this is not a probability distribution in the sense that it's not a function of x, it's a function of theta. So it assumes that x is fixed. And it's a function instead of the parameters. This sometimes sounds like semantics, but it's important. For one, if I treated this as a function of x and I integrated it, I would get 1. If I integrate with respect to theta, I don't know what I get. It's just a function of theta, right? So it's a very different concept thinking of this as a function of theta versus a function of x. Okay. Then the second concept is that of a prior distribution.
Can you say again, like, what's the statement? P of x given theta, is this a likelihood that you find x given theta? Or
It's the probability that some sample x was observed given your parameter settings at theta.
Okay.
But importantly, treated as a function of the parameters, not as a function of x. So what we're going to usually do is plug data in, which we actually have in hand, and then tweak this thing. Okay, so the prior distribution is some probability over parameters. And this gets a lot of people stopped up. If I have a model and I have some parameters, how do I know what my belief about the parameters are before I've seen any data? I don't want to worry too much about that right now. You might say, I know something about my system. So let's imagine that I know that I have a model that is overly complex, and I'm allowing it to look at too many aspects of x, and I know that only a couple of the parameters are going to be present, and most of them are going to be 0. So I could have a prior that encourages, say, sparsity of those parameters, if I knew that. So let me imagine that you put some domain knowledge in here. If you don't know anything, then what you would like to do is have something called an uninformative prior, which is interesting, especially from a physics perspective, but I don't want to go into that in these lectures.
So when you're limiting your model to, let's say, few parameters, that's like having PSA, right?
Right.
Like zero, you're not gonna, you don't need the complexity to 20th order, you don't need it to 10th.
Right. So there are different ways of encoding that kind of information. You can encode it in the choice of the model that you use, or in the prior, and those are kind of different. In particular, maybe I'll come back to this. If you encode it in the structure of the model, maybe you want to think about that kind of like working in the canonical ensemble. And if you put it here, and then you have some way of encouraging things to go to 0, it's kind of like the grand canonical ensemble. And usually, this is a better way to work. Yeah. Okay. So finally, what you actually want to do is infer values of your parameters from the data, right? So what you want is the probability, or I'll write it down first, it's the posterior distribution. You want the probability of your parameters given your data, and just from the basic rules of probability, that's can be written in this way. Okay. So I didn't do anything here except just use the rules of probability, and this is the quantity that we care about. There are a couple of things to say here. This denominator is just normalizing the distribution, and oftentimes if you have a big model, theta space is very big, so you can't do this integral. You can't normalize, and maybe you can get away with things because what we care about is the functional dependence of this on the parameters only, and there's no parameter dependence here anymore, so maybe we don't worry about that so much sometimes. And also, notice that this is a distribution of parameters given data. And what I said yesterday and what we talked about when doing gradient descent and its variance was we're finding a value of the parameters from the data, right? So in this context, that seems weird. We're outputting not a setting of the parameters, we're outputting a distribution of the parameters. And sometimes that's what you want. And you could imagine making predictions with your model with particular parameter settings, and then averaging those predictions with respect to this distribution of parameters. And that would be the proper thing to do if you wanted what you would call a full Bayesian treatment of a problem. That's often not done because then you have to do an integral over the parameter space, which is very high dimensional. So what you would like to do from this is to give some summary statistic that says, I need a setting of the parameters. Tell me what to use. And you need to extract that from this distribution. So there are two things that people often output. Someone throw out some ideas. What would you use? So I took AP statistics in high school, and I learned properties of a distribution. I learned the mean and the median and so on. Maybe the mean and the mode are the ones that people usually output. So
Nobody uses kuriosis.
Kurtosis, yeah. So one thing that you might have is the average of the parameters, which would be just the integral of theta p of theta given x. And this is called the Bayes estimate. But this is problematic still because I still have to do an integral over theta. So maybe this is not the best single number to output. The other thing that you can do is take the take the argmax of this. So you can take the argmax over theta of p of theta given x. Okay. And this is called the maximum a posteriori estimate. As I'm writing this, I realize I forgot to tell you something above here. So if I want to work without a prior, if all I have is a likelihood function, you could still treat this as a function of parameters and maximize that and find the value of the parameters that make the data most likely. So if you do that up here, this is called the maximum likelihood estimate. Okay, does this all make sense? So I want to put these two estimates in the context of yesterday's discussion about bias and variance. In some sense, this maximum likelihood estimate, even though we're talking about a fixed model complexity, tends to live in this world of higher variance, lower bias. You're really subject to the fluctuations in the data. Whereas if you have a prior distribution that tells you something about what you think is going on with these parameters, you can bias yourself to certain kinds of parameter choices, and you'll end up like this this black region over here, where you won't get the right answer because you're encouraging the parameters to be different than what just the data alone tells it, but you'll have lower variance. Yeah.
So when you're doing this maximum likelihood, so the theta is the optimal value to maximize px of theta. What is theta ML?
Yeah.
Maximize
P of x given theta. Yeah, with respect to theta.
That's a function of x.
It depends on the data, absolutely. Yeah. So remember when we derived the bias variance decomposition yesterday, the theta hats were functions of the data set. And that's certainly going to be true here as well. Okay. So let me give you an example of this.
Can you comment again in
Yeah.
relation to what you were doing yesterday? So you were optimizing, some cost function, or minimizing some cost function. What is that in relation to
in principle, that could work for either this or that. So we just wrote down C of theta and then said theta hat is argmax of C. I didn't say what C was. And I wanted to keep it general because I could plug in C is this posterior distribution, or C is the likelihood function. And the argument of sense. Yeah. Yeah.
Can you please remind me what's the main difference between these two? Which one is computationally cheaper, or I don't know why you choose which
Yeah.
one's better?
I don't think there isn't one answer to which one's better. All of these, so these two are on a par with each other in terms of computation, in the sense that you have to maximize a function with respect to theta. So you have to maximize in whatever dimensional space theta is. This one is problematic because you have to do an integral over this high dimensional space. Yeah. Okay. So let me give an example of doing both maximum likelihood and map estimation in a very simple, concrete sense, and that's linear regression. So the idea in linear regression is, imagine that the data itself was generated. So the data itself is generated in the following way. Where we have some inputs x. There's some, I'll call these W stars. And we take the inner product of the dimensions of a sample x with W, add some Gaussian noise like we did yesterday, and get a y value. And we have a data set of samples x, y from there. Okay? What we're going to do is have a likelihood function P of y given x and some model parameters theta that is a normal distribution that for the output y given a mean value of mu of x and a variance sigma squared, which we'll assume to be constant. So we want to find a way that we can take an input sample x, output a mean of some Gaussian distribution that with some fixed sigma will fit this data. And in particular, we want to choose a simple functional dependence for mu that's just linear. So mu itself is x transpose w. And now our parameters are the set of the weights in w and also the sigma squared. Okay? So what we're going to do then is let's first do maximum likelihood, because I gave you a likelihood. Now all we have to do is optimize that likelihood with respect to parameters. And there's a little switch that is almost always done here, which is rather than maximizing the likelihood itself, you maximize the log of that likelihood, because log is monotonic and it turns sums into products into sums. So we want to find settings of our parameters that are the argmax over theta of the log of this likelihood, right? And since this is a Gaussian distribution under our modeling assumption, we can write that as So we can write it in this way where we have a sum over the squared differences between what the model is predicting and the true data that comes out. It's scaled by 1 over the variance of the Gaussian, and then there's a constant term which depends on the variance as well. And then what you would do is you would, as we say, we would maximize this or minimize, because of the minus sign, the squared difference. And I'm not going to go through that. In this case, there's a very simple analytic solution, so you don't need to do the stuff that is hidden under the board here for gradient descent. You can just write down in one shot what the answer is. But actually, even in this case, there are interesting properties of gradient descent. So if you don't have enough data, then this problem is underdetermined, and there are many different parameter settings that give you the same level of performance. And you could ask, what happens when you run gradient descent in that case? Which of the solutions does it pick? And it actually turns out that it picks solutions that regularize your model in interesting ways. So just an aside there. OK, so this would be doing maximum likelihood. What if we instead want to do a Bayesian treatment and have a map estimation? So what we need to do then is we need to have a prior on the parameters, in particular for W. And there are different choices that are often made. So the two that I'll mention today are you might imagine that your parameters should be kind of small, so you'll penalize when they get big. And you might penalize them with a Gaussian. Why a Gaussian? We can debate that, but this will just say if you want to have a large parameter when we do a map estimation, you can, but your data better justify it. Otherwise, I'd like to make you small. And an intuition behind this is that once you make parameters big enough, you can start having different terms that are pulling very, very strongly in opposite directions, and you're able to fit a lot more wiggles once you make parameters very large. Another option would be, instead of a Gaussian, just have an exponential. And this, it turns out, will encourage your parameters to go all the way to 0 if they're not being used. So this will end up sparsifying your parameters. So if you do that, and then you look at the map estimate, I'll write it down, say for this one. Then what we want to do, again, is the argmax of the log, but not of this quantity, instead of this quantity. And thanks to the log, this becomes a sum of two terms, right? And the first term is what we saw before. And the second term, down here, is going to be something that you probably have seen before. So you end up getting something that looks like the L2 norm of the weights for this case. Yeah.
Is that pi I product?
Oh yeah, sorry, this is product. So every parameter, and in particular, I should be writing this as just a prior on the W's, not on the sigma. Okay, so then you end up with something that trades off between trying to fit the data as best as it can, while also trying to have the values of the parameters be small in an L2 norm sense. If you use this instead of this, then instead of this being the L2 norm, you get the L1 norm. And this is called ridge regression, and the L1 norm is called lasso. And I wanted to give you a couple of plots for what happens when you try and fit models with using these different regularizers. I guess, sorry, I just used a term that I haven't introduced. So this now is an extra term that is encoding our prior information or our belief about what the parameters look like, and it has the role of pulling you away from fitting the wiggles of the data, and in some sense they're called regularizers because they regularize the result of the learning process to be less dependent on the realization of the data set. And again, in this sense, they add bias and they decrease the variance.
How is it different? How is its effect different than the noise? It seems like it's very similar.
The noise.
So you have this sigma. I guess sigma doesn't depend on anything.
Yeah, so I'm actually imagining not worrying about optimizing sigma here, but once you optimize W, you could optimize sigma as well, or you can do it together.
But what I mean is the noise in the data has this, seems like it has the same effect in that it's pulling you away from trying to go through all the data.
Well, the noise in the data is adding, to go to some of these that are easier to look at. The noise is adding structure that is fictitious, and the model wants to fit it if it can, right? And the regularizer is trying to prevent that from happening. At least that's the story that I'm supposed to tell. Yeah.
Can you define regularization, and also can you use SVD for regularization?
In certain contexts, yeah. I was planning on saving the discussion of regularization for next lecture, actually. So let me leave that here. I mainly wanted to show this in the context of Bayesian inference, and that there's an equivalence between having a prior and having these things that are called regularizers that give you a bias that says I think my parameters should look like this or something like that. Okay, so let me just give you an illustration of what happens when you do this on some toy data set that you're probably familiar with. So imagine that, let's see, where am I? Let's say you want to learn the Hamiltonian of an icing model. So let's say that you have an icing model which is a 1D icing model. There's some coupling, and you have some nearest neighbor connections between your spins, strength J. And we're going to generate a bunch of samples from this icing model. And we're going to have the model try and learn the Jij matrix of all pairwise possible connections when all I do is give it the individual terms here as the input and the energy as the output. So I'll try and explain that. So our model doesn't know that things are one-dimensional. So we're going to sum over all pairs, of potential spins. And then the X data that we're going to give is all of these, all of the pairwise products. And then we want to learn the corresponding coefficient for all of these n squared numbers. Does that kind of make sense? And we're going to do it with linear regression, which I guess I have behind. Yeah. And I want to do this with ordinary linear regression, and then I want to see what happens when I put the different regularizers on. So I apologize for the legend on this plot, but so here what I'm plotting is the degree of accuracy in predicting the energy on test samples when I do different methods, and I choose different values of this parameter that tells me how much I care about my prior term. And for the regular linear regression, which doesn't have the prior, it's just doing maximum likelihood, there's a value. And on the training data set, you get perfect prediction, which is the blue solid line. When you look at on the test samples, which is the blue dotted line, it does much worse. It gets 0.6 with this measure. And that there is no lambda parameter because it's just maximum likelihood, so it's just a constant. If you do this with the with ridge regression or putting a prior that is a Gaussian on the parameters, for small values of lambda, it does perfect on the training set, and then it starts to degrade once you make the strength of the regularization parameter very large. And on the test set, it does the same as regular least squares, and then degrades away. If you do that instead with the prior that the parameters are Gaussian distributed, which I was saying encourages sparsity, what you find is that there's an intermediate regime of this strength of the prior term, where the training and testing are both essentially at 1, and then it degrades very quickly. So that's interesting.
That's exponential.
Sorry?
Not Gaussian, that's exponential.
Yeah, sorry. The green one is for the exponential. Yeah, sorry. And if I plot here the learned Jij matrix from doing this exercise for ordinary least squares with no regularizer term, there's a off diagonal nearest neighbor component that it captures, but it has a huge amount of background noise, right? If I use this ridge regression, it kind of looks the same. It doesn't really do much better, which is consistent with the idea here that the result here that the Gaussian prior is not really helping you get better performance. Whereas if I look at the exponential prior, what you find is that for some intermediate value of the strength of the regularizer, all the noise in the background is gone, and all you see is this nearest neighbor thing. So it actually recovers the structure of the underlying model. So this connects back to what we were saying, what I was saying in the last lecture, that yeah.
R is your error.
R is performance.
So you want R to be 1 or 0?
1 is good. Sorry.
One is good. Okay.
Why are you
So why
your
does
mesh is
last-
not symmetric?
We just didn't enforce them to be symmetric.
So why does lasso do badly?
Um,
No, it does badly.
Lasso does badly. Oh, sorry, no, Lasso does well.
So 0 is good.
No, so this is hard to see, but Lasso is in green, and the test in green is what we care most about. So the dotted one, and that goes up to 1 for, say, value of 10 to the minus 2, where it's actually recovering very good predictive performance on the test set, and that corresponds to the case where it actually is recovering the correct structure in the model. And it's interesting that happens in this case, but I want to caution again that these methods in machine learning are meant to be able to make good predictions. It's meant to be, I can make good predictions on my test set over here. There's no promise that when you open it up and look at the model that it is the model that reproduced, that generated the data. In this case, it happens to be true, but one of the reasons why that's true is the true model was within the class of functions that we were allowing it to compute, right? And for a complex system, that's never the case. And you have to deal with the fact that you can make good predictions without having the right model in hand. Okay. Yeah.
Before you move on, can you do the whole Bayesian model comparison thing and show that, I mean, so since we know what the right answer is, you can point to that one thing and say, oh, see, if you choose the right value of lambda. Alternatively, if you do the testing, you can find out. But if I just give you a training set and say, go for it, right? So you don't know how the tests are going to turn out. Is there a way of figuring out that by doing model comparison that class of compute the total probability of the data in the class of models by integrating over the parameter, right?
Yeah.
Data. Can you convince yourself that lasso is better than ridge and that the value of lambda in that range is the right one?
Right. So I don't know the answer in this case, but in principle, perhaps. So I wasn't planning on talking about these model comparison this model comparison literature, but there are ways of doing what you say, and if you do it the way that you suggest, that you end up with a term that corresponds to something called BIC for Bayesian information criteria, which tells you if I have so and so many parameters, how much better do I have to perform to make it worthwhile to have those extra parameters. There are other kinds of criteria. There's one called AIC for Aikiki information criteria that is similar but a little bit different. There's one called Takeuchi information criteria, which is a version of AIC that seems like it's better. The reason why I wasn't talking about these is that in particular, so this requires you to look at something like the determinant of the Hessian matrix or something like this. And since that's intractable for big models, I want to encourage the cross-validation as opposed to using a model selection criteria. Yeah.
Do you understand why there's such a drastic difference between exponential and Gaussian? Did you explain that? Or?
So I didn't. So I skipped over one set of pictures that people usually show for the interest of time. But what essentially is happening when you use these different these two particular priors is if you have the Gaussian prior, you end up with parameters that would have been like this, but then are just sort of scaled down versions of what you had before. When you use the exponential prior, what you find is that if you were going to have a parameter that was going to be small enough, it actually gets shunted down to 0, and you end up with this whole region which is controlled by the strength of lambda that will set all those parameters exactly to 0, which in the case of the 1 de-Ising model where you have only n out of n squared non-zero interactions, it'll cut those out.
It makes them all non-zero, but maybe small.
That's right. Yeah. So it's not going to encourage these to go to 0.
But just maybe suppressed. While here, really, for exponential one, it really gives you a solution where all like nearest neighbor are 0. Is that what that?
Essentially, yeah. So for all this background of small things, Ridge is just going to say, oh, you wanted to be this small, I'll make you this small instead. But here it says, oh, you wanted to be small, I'm going to make you 0. So when the true interactions are sparse, that's a good prior. And we chose a model where it was a negligible fraction of non-zero interactions. So this was a good prior in a sense.
Can you go back just one slide back?
Yeah. other way.
So why is it for the green, I guess, lasso, why does it, for large lambda, it's doing badly even on the training set?
So when you make lambda big enough,
Is it because it's not fitting well?
yeah, that's there you're underfitting.
Oh, I see.
Where did I go? Is there something up there? I think I'm hidden under here. Yeah, so now you're trading off minimizing these two terms with respect to W, and if you make lambda large enough, it just won't care about this anymore. And it'll just shrink everything down to very small values. Yeah. If you ran this exercise in the 2D icing model, you would still have order n interactions and n squared possible partners. So lasso would probably be good.
How about like higher? I mean, I guess is there a dimension in which
If you tried to do this for a potentially all-to-all coupled system like a spin glass or a neural network, this would be a terrible prior. Yeah. But I guess for any finite dimensional system, you'll still essentially have order n interactions.
You may want to change the title of the slide.
Oh, sorry. Yes. Yeah. Go ahead.
But at some point, shouldn't your dimension become large enough that because of the course of dimensionality, the course of dimensionality, both the models would be the same because at that point everything is kind of on the surface?
Say this one more time.
I mean, in low dimensions and things like lasso is better, but if it's a high dimensional system, this is going off of the previous question, wouldn't at some point both of them, ridge and lasso, behave the same way because you would only have so many nearest neighbors? Or is that not true? Maybe I'm...
They might have similar performance. They will give different answers because they will affect your parameters differently. So lasso will still have more sparse ones, more zeros, and so on. So my objective in presenting this is not to try to sell you that you should go use ridge and lasso on every problem, but rather the connection between these terms that you see added to your objective function and priors that you assume on your parameters. Yeah.
Is there an interpretation to the parameter lambda? Is it reflecting a property of the data? Can you make a good guess without ever doing cross validation?
If you know something about the data, then yeah.
Is it reflecting the variance or some other property of the data, or
So in the lasso case, it reflects the degree of sparsity that you expect. So if you know something about the degree of sparsity, then you could intelligently choose lambda. But usually one sweeps over values of hyperparameters and looks at performance on another set. Cool. Any other questions on this? I want to briefly introduce, if I have time.
9 minutes.
9 minutes. Maybe I will save this actually. So the plan next was to briefly introduce logistic regression, which is about making predictions on discrete data instead of continuous data. So oftentimes, the canonical example of making a binary decision is distinguishing cats versus dogs because they both are fuzzy and have ears and noses and eyes. So it's not obvious like what distinguishes them. By the way, I have on here my take on the cats versus dogs debate in terms of what's signal and what's noise. But anyway, so we're going to introduce logistic regression, both because it's what's that?
Stand up and then
Right. So in the past, people designed features like that and said, oh, cats have ears that stand up and so on. And then you could fit a logistic regression model that would get good predictive performance. But it turns out that finding the right features is hard. Nonetheless, the language of logistic regression and framework is central to the design and architecture of neural networks. So I want to introduce this in the context of connecting logistic regressors together and use that as a segue into neural networks. But I'll save that for next time, and maybe we should have any remaining questions about today's material.
Why don't you start?
Start with logistic regression? Yeah, I might be able to get through. Okay. So our task here is to come up with a way of deciding whether something is class 1 or class 0, say, or the other way around. And before getting to the point where we can make such a binary decision, let's imagine we stick with a linear model like we just had, where we have something I'll call S that takes the data or features of the data times some set of parameters plus some offset. And then what we can imagine doing is make a decision based on some nonlinearity that takes in this number S, which is anywhere on the real line, and outputs just a 0 or a 1, or 1 or minus 1. And this is what a perceptron model could do. So that's the term for this kind of object. What logistic regression does is a sort of softer version of this. So instead of having a sharp decision where you say, if S is less than something, you're class 0. If S is bigger than something, you're class 1. It sort of smoothly goes between one and the other. So this is a perceptron. Instead, if we have sigma be something that looks like physics, then as S goes from minus infinity to infinity, our predictions will go from 0 to 1. Right? And there are various ways of justifying this in terms of log odds, and that's actually where the term logistic regression comes from. But in 3 minutes, I'm not going to go there. So in particular, what we assume is that the probability, say, that a sample is in class 1 given the image of the cat or the dog is 1 over 1 plus e to the minus xi transpose w. Plus b. And then what we can do from there is write down a likelihood model, and then we can maximize the likelihood. So that's what we're going to do. So to write down the likelihood model, we need to say what is the probability of the data, say, given my parameters. And what you do is you write this as a product of all of the data, where you look at the probability that that the model thought that the output should be 1 times the probability that the model thought that the output should be 0. And this is kind of a funny equation, but essentially what it's doing is if I have data that is inputs of images of cats and dogs and outputs of ones and zeros for whether they are cats or dogs, it will pick out the term that is whether it was a cat or dog, and then look at the probability that that the model thought it was a cat. So this is our likelihood function, and then what we do is we maximize the log likelihood as the cost. And in 1 minute, I'll write it out because it's an important equation. So it's the sum over the data samples of minus yi log sigma minus 1 minus yi log sigma 1 minus sigma, sorry. And this quantity is called the cross entropy, and we're going to come back to this next time. And so what you would do to learn this model is you would take the gradient and then do gradient descent or stochastic gradient descent or whatever. It turns out that you can compute the gradient here, but you can't set it to 0 and solve for the parameters. It's a transcendental equation. So there's no closed form solution like there was in linear regression. So you actually have to use a gradient-based method to fit this model. But it turns out that it's also convex. So you can use a gradient-based method and get the global minimum. Did I lose a minus sign?
If you want to minimize it, you minimize it.
This, in addition to this minus sign? Oh, I have maximize.
Okay, so why do you put a minus sign down there?
Fair enough, true. Good. Okay. So I think we're out of time, so I should stop here. But generalizing this to in cases where you don't have just binary outputs of 0 or 1 to multi-class outputs, and then turning this into a neural network is where we'll start next time. So, thank you.